Alright, space science and astronomy class. I'm going to do some notes here on relativity. Some of this is already covered, so that stuff I'm just going to breeze through. And cover a few other um, characteristics or traits, facts about special relativity before we do a couple of fun assignments and then ultimately move on. Only have a few weeks left, especially for those of you guys that are seniors, so I'm going to try and keep things pretty brief. Okay, so special relativity obviously has to do a lot with light and the speed of light. Okay, remember that, you know, the light can only travel at the speed of light, not faster, not slower. We typically represent the speed of light with the small letter c. Now, the speed of light is super fast, unfathomably fast. Something about 180,000 miles per second. Not miles per hour, miles per second. Or about 3.0 times 10 to the 8th power meters per second. That comes out to be about 300 million meters per second. Or as a frame of reference, that's about 8 laps around the Earth's equator every second. Okay, so even at that speed, the distances in space are huge. Okay, so light from the sun takes 8 minutes to get here. You could say, in other words, you could say that the sun is 8 light minutes away, as opposed to light years. The closest star is 4.1 light years away from us, 4.2 maybe, which means that the light from it, traveling at the speed of light, takes 4.2 years to get to us. Most things in space are, much thousands, millions, billions of light years away. Okay, and that's just kind of how light works. Okay, so in 1905, Albert Einstein was a young man. We used to see him as this old man with this gray wild hair, but he was only 26 years old. Okay, young guy, and completely reinvented science out of nowhere. He wasn't even a scientist. He had a desk job working as a clerk at a patent office. And he wrote 4 different papers that basically changed science forever. Okay, for our purposes, most of these we don't really need to talk about right now, although they are very interesting. But the first one is what we were talking about right now, the theory of special relativity. And basically, the theory of special relativity basically changed everything we know about everything. It changed how we think of everything. Okay, and basically, the theory of special relativity said that space and time are relative to an observer, which is totally surprising. Space is space. 1 meter for me should be 1 meter for you. 1 mile for you should be 1 mile for me. 1 minute for me should be 1 minute for you, and so on and so on. That's not true. To be relative to something means it depends on perspective. Both space and time are these fluid, changing things that depend on perspective. Now, these are so important because these are the correct laws of the universe. Okay, everything you learned in some science class about Newton's laws aren't actually right. At certain extreme conditions, Newton's laws break down. Einstein's laws of motion are always right. And that's kind of how he thought of these things. He kind of imagined extreme scenarios. What if you could travel at the speed of light or very close to it? What would the universe start to look like? And when he started posing weird questions like that, what would it be like to travel at the speed of light? He realized that the normal rules for the universe don't make any sense. And so he knew he had to be a problem, and so he created some new ones. Okay, so as I said, the theory of special relativity means that space and time are both relative. And Einstein realized that space and time are one thing, 2 parts of one thing. Okay? When you travel through, the faster you travel through one, the slower you travel through is another. Okay, but sometimes in movies you hear the fabric of space-time, and I guess that's a thing. But they're referring to space-time, okay? It's one word, space, one hyphenated word, space and time. Space and time is this kind of fabric we exist in. It is not matter, it is not made of atoms, it does not have mass, but it is this structure that we exist in. And space and time exist together. Space you could define as where things exist. Time is kind of a little trickier to define, but usually defined as the passage of events. There's no time, there is no events, there are no happenings. Okay, now the universe, space-time exists as part of the universe. So when the universe was created, space and time was also created. So there was not time before the Big Bang and when the universe was created. Now that's not just saying like some weird thing like, oh, the land before time. No, like time, the entity of time, the passage of events did not happen. And it's not one of those, oh, if you weren't, if a tree falls in the forest and no one's around to hear it, did it really happen? Which is one ridiculous question. Of course it happened. But that's not even what we mean. It's not a perspective thing. It's just time itself did not happen. Time itself literally began 13.8 billion years ago when the Big Bang happened. So they are the same thing. They are two parts of the same thing. And the faster you go through one, the slower you go through the other. These two I already covered on the earlier assignments. The first postulate, I'll give you the short version, basically says there's no difference between being at rest and moving at any constant velocity, whether that be 10 miles per hour, 100 miles per hour, 1,000 miles per hour, 100,000 miles per hour. There is literally no test you could do within that frame of reference at any constant velocity, meaning you're moving at a constant speed in a straight line, that would wind up any different than being totally at rest. Now that has to mean that there is no physical difference between the two things. The two things are the exact same. And that's what we refer to as an inertial reference frame. It is basically a constant velocity frame of reference. So if you're riding on a train moving at 50 miles per hour in a straight line, that's an inertial reference frame. You are sitting here at rest doing nothing. That is also an inertial reference frame. The second postulate, again, I've already explained this, speed of light is always the same. No observer can, no observer can ever observe the speed of light to be going faster than the speed of light or slower than the speed of light. The speed of light is a universal constant, okay? It always has to be the same. If it weren't the same, always, a lot of weird things that we don't ever see happen would have to happen. Like we would see events happen before they happen that never happened. That just even saying that doesn't make sense. And again, some of this was already explained in the early assignments. I don't want to repeat myself too much and waste your time. But, light is not the same thing as like when you throw a baseball from a moving car. The speed of the baseball doesn't, adds to the speed of the car. But instead of throwing a baseball, we shined a beam of light in front of the car. The speed of the light does not add to the speed of the car. And that's kind of what this second rule is saying. So some of the effects of these, the last part got cut off here, are time dilation we already talked about, as well as length contraction. Okay, so really quick summary of special relativity. Now, first note that we call it special because it's specific. That's what the word special means. It is specific to the case of constant velocity. And constant velocity means at rest, too, because that's a constant velocity of 0. These rules do not apply to accelerated objects, things that are speeding up, slowing down, going around taking a turn, that kind of thing. So, in summary, space and time are two parts of the same thing. Time, like motion, is relative to the observer. It depends on perspective. So different observers can observe or measure different amounts of time going by. Speed of light is always constant, no matter what the source of the light is doing, no matter what the observer of the light is doing. Any of that, speed of light always has to be measured as c, the speed of light. Use my little pointer here. Because of these, there are some unexpected consequences that we see at speeds close to the speed of light. Okay, now this was a scenario I talked about in the one worksheet. This is basically an event that doesn't happen, that if the speed of light wasn't constant, we would have to see it happen. You have an observer here, observing a car crash. Car B here is about to collide with car A. They're headed towards each other, same speed, towards this collision point. Because car A is headed towards you, if light worked like anything else, c, the speed of light, would add to the speed of the car. The light from the blue car would be getting to you faster because it is moving faster. It would be moving faster than the light from the red car. This, in effect, would allow you to see the blue car move into the collision point and through the collision point before this collision ever happened. This collision, it has to happen. It always happens. How could you possibly see this move through here before it ever happened? This is not something we ever see. And this is why the speed of light has to be constant. The speed of light from the blue car, as well as the speed of light from the red car, have to be 100 miles per hour. So the speed of light does not add to the speed of this car. So you can't see events happen that don't happen before they happen. Again, that doesn't even make sense, and that's kind of the point. This is one of those thought experiments that Einstein did. And, skip that one, I guess. Okay, time dilation. Basically, time dilation is a fancy way of saying time travel. Time dilation means that two different observers move through time differently. Common way to explain this is something called the twin paradox. A paradox is a term that basically means any problem, any hypothetical thing that doesn't make sense. It's like a question that doesn't really have an answer. So with the twin paradox, you basically have two identical twins. These guys both the same age here. One goes on a spaceship, travels away at a high rate of speed. He comes back, and he's mostly the same age, but his twin brother is now much older. His twin brother has maybe, say, experienced 70 years of life, while the other twin, the traveling twin, has only maybe experienced, say, 40 years of life. They're twins, but they are different ages by decades. That doesn't seem like it should make sense, but that's what happens in these situations where you travel at really fast speeds. The underlying principle of time dilation is that fast clocks move slow. The faster you move through space, the slower you move through time, according to somebody observing you, at least. Your clock always runs normally. You think, you're never experiencing a fast forward time or a slow motion time. You are always experiencing time run at the maximum rate that time can run. And that's the rate that time is running for you right now. 1 second, 2 seconds, 3 seconds, tick, tock, tick, tock. That's how fast your and my clock is running right now because we are at rest relative to ourselves. I'm not moving further away from myself or closer to myself. I am at rest relative to myself. So I am moving at the minimum rate through space, which means that I am moving at the maximum rate through time. However, if I move at a faster rate through space, according to somebody else is observing me and I'm moving away from them at an incredible rate of speeds approaching the speed of light, then their observation of my time slows down. And it's not just a tricky observation thing that actually happens. We are disagreeing on the amount of time going by. This is time travel into the future. You cannot time travel into the past. That would create all kinds of problems for a variety of reasons. But so most movies that have backwards time travel kind of just ignore the fact that things stop making sense. But you can't you can't travel backwards in time. So dilate, remember, like when you dilate your eyes, that means to expand, to widen. Okay? It's kind of the opposite of the word contract. Contract means to shrink. Dilate means to widen. And that's what we're doing here, is we are stretching out time. Here is another reason the speed of light had to be constant. I don't know. I already talked about the other assignment, so I'm not going to bother talking about that now. Hopefully by now you've already completed the Planet of the Apes episode. Hopefully you thought that was a little, or episode of the movie, you thought that was a little bit neat. But again, it's a very famous scene, and so much so that it was parodied in Simpsons. This probably won't show up very well here, but there's an episode of The Simpsons in which Homer became an astronaut, and then he's trying to explain himself to the press here.
Question for the barbecue chef. Don't you think there is an inherent danger in sending underqualified civilians into space?
I'll field this one. The only danger is if they send us to that terrible Planet of the Apes. Wait a minute. Statue of Liberty. That was our planet! You maniacs! You blew it up! Damn you! Damn you all to hell!
Thank you, I'm afraid that's all we have time for.
Great episode of The Simpsons. Again, I don't know if that...
Question for the barbecue chef. Don't you think that...
Sorry about that. Playing a video within a video. I don't know if that showed up well, but like I said, the Planet of the Apes thing I showed you because that was appropriate. That's exactly what happened. Is the main character, the astronaut, experienced time dilation and didn't realize it. He had traveled so far into the future that he wound up many thousands and thousands of years into the future on Earth, where apes had taken over and humans had devolved back into the lower life forms, presumably because they had ruined what they had. They had ruined their chance. They ruined the Earth, which is a beautiful gift that the humans were given. So there's kind of a great underlying message there. Under the kind of silly premise of a Planet of the Apes and like these 1960s apes costumes, and so the whole thing was silly, but a very classic, well-known science fiction movie, of which they've remade most of them in recent years in different ways. So a few things to keep in mind about time dilation. As I said, every observer feels their time running normally. Like I said, you can only be moving. You can only be moving at the maximum rate through time, because we are moving at the minimum rate through space relative to yourself. So no observer would ever see another's time running fast. Say you're watching somebody on a spaceship travel away from you at really fast speeds. You see their clock running slow. They look back at you. They see your clock running slow. You each think the other person's clock is running slow. So who's actually running time slow? It winds up being the person that experienced an acceleration. And that's a little bit beyond what we're talking about right now. But you are never going to see another person's clock going tick-tock, 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 tick-tock. You will only see it going the normal rate, tick-tock, tick-tock, or slower, tick-tock, tick-tock. And the faster that space traveler is going, the slower that clock gets. You are watching it from Earth, and you have a space traveler going at very close to the speed of light. That clock isn't just going tick-tock, it's going tick-tock, tick. Their time is running slow. The moving space traveler is moving forward through time. So speed of light has to be constant. If it's constant, basically that means that something else has to give, and that something else has to give is time. Okay? So here's a stationary clock. I don't know, they do this light clock example. They talked about it in that one video with the laser beam. It's just a really good extra explanation for why this has to happen. Is that a moving, if you have a hypothetical light clock and a beam of light bounces here to there, and each time it bounces, these are two mirrors, bounces between here and here, it's a tick and a tock on the clock. So here's an at rest one, boom, boom, and here's a moving one, tick, tock, tick, tock, tick, tock. This path is longer than this path. Now, since the speed of light can't be going faster, that must mean that we would observe more tick-tocks going by on the at-rest clock than we would on this one. The speed of light cannot be going faster, so this clock has to be slowing down. And the faster this clock moves, the more stretched out its path is going to be. And so the more of these tick-tocks are going to go by in between each tick and each tock on the moving one, for the faster this is going. This is an equation. We don't need to worry about this. I just show this because it shows you why the speed of light, why there is no difference in the two amounts of time until the speed of light, until the traveler is going at the speed of light. So this is the Earth's clock. This is the spaceship's clock. Now this term here explains how much difference there is between the two times. 1 divided by the square root of 1 minus v over c squared. So v represents the speed of the spaceship, c represents the speed of the light. Okay? So if you're not moving like you are now, presumably, v is 0. So v squared over c squared becomes 0, and you have 1 over the square root of 1. Square root of 1 is 1, and these two numbers are identical. And if two observers are at rest relative to one another, those two numbers wind up being the same. However, if this speed gets really, really close to c, then this whole bottom term gets closer and closer to 0. Right? Which means that there's going to be more and more disagreement between this term and this term. But even if you're going at a pretty fast everyday speed, like say 100 meters per second, you have 100 squared over 300 million squared, this term still winds up being pretty much 0. And 1 minus 0 is still 1. And so 1 over the square root of 1 is still 1, and there is no difference. So until this number here get kind of close to c, the speed of light, 300 million meters per second, there is not going to be much or any difference between the clock that goes by on the Earth, or excuse me, the clock that goes by the spaceship's clock relative to the Earth versus the Earth's clock relative to the Earth. Okay, so again, don't worry about, we're not going to do anything with this equation. I just want to show you that unless you are going at speeds very close to the speed of light, the amount of time dilation is negligible. It can be ignored. It's almost imperceivable. And this is a graph I showed you in the one worksheet that we did, is that shows you here. Down here, if you're going 20% the speed of light, 40% the speed of light, 60% the speed of light, 80% the speed of light, here's the speed of light. There is no difference between how much time the two observers experience. Even at 20% the speed of light, there's barely anything. The fastest a human has ever gone as a percentage of the speed of light is like 0.0004% the speed of light or something like that. But like say at 80% the speed of light, which is incredibly fast, speed we'll probably never ever get to, that means that if the 2 years go by, we'll say closer to 90, so we're looking at a data point here at about 90% the speed of light, that means that 2 years are going by for Earth for every 1 year that's going by on the spaceship. So that means that if I was the one going in the spaceship, then I went away for a year. I experienced every second, every minute of a year, and I would come back. It would be 2 years later on the Earth. But that's not really that interesting. What does get interesting is if we really multiply that number. Okay? So this little calculator is kind of a cool thing. Okay, so I'm going to enter 1 year in here. So say I'm a space traveler. I leave for 1 year relative to me. And I'm traveling at 90% the speed of light. So I enter 0.9 there. When I hit calculate, this is how much time goes by for Earth. A little over 2 years. Okay? So I would travel. I was only gone for 1 year, but 2.3 years passed on Earth. Now, if I keep adding 9s here, so here, this is 99% the speed of light. 1 year goes by for me. I would leave for 1 year, and I would come back, and it was 2027. I add another 9. I do this one. This was my favorite, because if I went away for 1 year, traveling at 99.9% the speed of light, which is allowable, the laws of physics say that you can do that, it's just really difficult, I would come back, and it would be 22 years later. It would be the year 2042. And funnily enough, I would come back, you all would be older than me. Okay, I'm about, 17 years, 18 years older than you all. And I would come back, and I would be, 1 year older, so that would make me 37, and you guys would all be 40. 39, depending on how old you are. And we can keep adding 9s here, and in 70 years, jump there. And hey, I did that at 99.999% the speed of light. And I'd go 22,000 years into the future. So this might be a Planet of the Apes scenario. Might have to add a few more 9s to get to that. Or in order for, a lot of time I'd have to go take back for apes and all that to happen. But you get the idea. Now, if I entered a 1 here, that would turn into infinity. You can't travel at the speed of light, but if you could travel at the speed of light, you could go anywhere in the entire universe instantaneously. Not even instantaneously. You would already be there. You would already be at that location. Light, and only light can do this, it travels through space without the inconvenience of having to travel through time. Which is crazy. Okay? So it means light is here, there, and everywhere all at once. It is omnipresent. And one thing I always throw out in class, it's kind of funny, is that, in different religious texts, there's always the phrase, God is light, whatever higher being that you may or may not subscribe to, there's always, they are the light. And literally, and one of the traits of a higher being is that they are omnipresent. They are everywhere. And that is exactly what light is, according to light. If light could think or whatever, it doesn't experience time. So that means it's here, there, and everywhere. It is literally everywhere, all at once, according to it. Not according to us. It has that time, of course, which is, I don't know, it's just kind of a crazy way of thinking of it. So here you see some cases of extreme time dilation. So feel free to go to that website. There's other websites that do this and calculate how much time dilation you experience, and it's just kind of crazy to think about. All right, scooting right along here. So in combination with time dilation, there is another effect that also happens. Okay, so with time dilation, it's kind of weird because this allows, because a traveler traveling at really, really fast speeds, relativistic speeds, this would in effect allow them to travel anywhere in the universe within a lifetime, essentially. At least according to them. So how is that possible? How are, say you want to go to the center of the galaxy, which is about 25,000 light years away. You might say, well, you could never possibly do that in your own lifetime because it takes light 25,000 light years to get there. So how could you do it with your own lifetime? You could, because you traveling at a really fast rate of speed, 99.999% the speed of light, time slows down for you. Just like how light does it instantaneously, time slows down for you. But according to Earth, it would have to take you at least 25,000 years. You couldn't get there faster than 25,000 years if it was 25,000 light years away. So it seems like you're going faster than the speed of light, but you're not. Time is changing because you're traveling really fast. Now this also works because, like I said, space and time are related. They're two parts of one thing. So when you're traveling at really fast rates of speed, time dilates, meaning expands, but length contracts, meaning the distance that you are moving through, space itself actually shrinks. And that's what allows a traveler that's traveling very, very fast to travel such great distances in such a short amount of time. So it's not the object, it's the space that the object is moving through. So if you have a meter stick, which is obviously a meter long, and it's moving at 87% the speed of light, then it would appear to only be 50 centimeters in length. It would shrink to half of its length. If a meter stick is traveling at 99.5% the speed of light, then it would appear to only be 10 centimeters in length. And we see that here. So here's the size of a ball at a speed of 0, 87% the speed of light, 99.5% the speed of light, 99.9% the speed of light. And if it could move at the speed of light, it would shrink to nothing. That, of course, is impossible. But again, it's not just the object. It is the space that the object is moving through, which includes the spaceship, the person, everything that moves with the object. It's crazy. Space and time are relative to the observer. So just like two observers can totally disagree on the amount of time that went by, two observers can totally disagree on the length of a moving object. So time dilation and length contraction are the two craziest effects of relativity. So really quickly, this will be the last couple things before I end this video. This actually happens. I can't emphasize this enough. This is not just some theoretical thing. We've measured this. There's 3 experiments I'll highlight really quick that do this. I'll maybe post this video for you can watch it, but in 1972, we put really, really accurate clocks called atomic clocks on airplanes, like the commercial airliners that you travel across the country or across the world in. They are accurate clocks that can keep accurate time down to nanoseconds. We synced them with at-rest clocks here on the Earth, flew them around the Earth, met them back up, and guess what? That even at the speeds, 500 miles per hour or so, that a jetliner would fly at, time changed. Time was running a little bit slower on the moving airplane. Now, it's an imperceivable amount. We're talking about nanoseconds, 0.0000002 seconds or something like that. Imperceivable amounts of time, but measurable amounts of time. People on a plane actually experience time differently than people on Earth. And again, not a mental thing, but less time actually passed for people on a moving flight than people that stayed on Earth. Crazy. We don't experience these things in our life, but this actually happens. We can measure this. So we measured it at relatively low speeds, but small amounts of time dilation. This is one I also mentioned before, is that we can measure this with really small things. Really small things, these subatomic particles called muons. We have these giant machines called particle accelerators. This is the inside machine. This is a famous one in Switzerland and France. Yeah, that's right. It's so big it takes up it's in 2 countries. See a little person there. But these giant machines are used to accelerate these small subatomic particles that are so small they basically have no mass. We're talking about smaller than an atom, smaller than an electron, and they accelerate them to speeds close to the speed of light, and then smash them into each other and see what happens. And that's how they do a lot of particle physics things. And this requires an entire city's, an entire state's worth of power to accelerate these almost massless things to the speed of light. These are the largest machines ever made, used to accelerate particles smaller than an atom. Anyways, one of these particles, called a muon, they have a known decay rate. This is their normal decay rate. Boom. When we accelerate them to 99.5% the speed of light, this now becomes their decay rate. They live longer. They're not really living longer. They're just traveling into the future. Time passes slower for them. So this is proof. And we're using the known decay rate of this particle called a muon as a clock of sorts. And if they're at rest, their decay rate always looks like this. That's their clock. But their clock is running slow because they're going at very fast speed of light. One more we can see the supernova. We look at supernova, we know that that's a remnant of an exploded star, and we can use the brightness cycle of an exploded star as a clock as well, because the supernova only stays bright for so long. If you look down here, the green curve represents, sorry, this graph got cut off by my display a little bit, but this green curve represents the brightness curve for a supernova that is at rest relative to the Earth. It peaks in brightness after about 18 days and gets pretty dim after about 40 days. The red line represents a supernova moving away from us at about 69% the speed of light. That brightness curve is elongated. It is traveling for a greater, or excuse me, it is living longer. It is traveling into the future. The blue line is one that's moving at 84% the speed of light away from us. And again, we can use that brightness cycle. It's saying, why are those ones always staying brighter for longer? They're not. It's just we are seeing their clock run slow. That supernova is experiencing time differently than Earth is. So, last thing here. Russian cosmonaut, I don't know if this is the same one that they referred to in the one other video we watched, but Sergei Devyev, Russian cosmonaut, 747 days in space, traveling 17,000 miles per hour relative to the Earth, and he traveled 0.02, or 1/50th of a second, into the future. Not a whole lot, but a measurable amount. So we do have space travelers, just they are kind of lame and can only go 0.02 seconds in the future. Light does not experience time. It travels through space without traveling through time. Whereas right now you are moving at the minimum rate through space, so you are moving at the maximum rate through time. Light is moving at the maximum rate. That is the speed limit for the universe. It is moving at the maximum rate through space, so it is the minimum rate through time, which is no time at all. Light does not experience time. So if you look at this next note here, light takes 1,000 years from our perspective to travel to something that is 1,000 light years away. But from its own perspective, that trip is made instantaneously. It's already there. Not even instantaneously. Not even an instant goes back. It's already there. And so the closer you can get to traveling to that speed, the closer that would become to being true for you. And, these satellites that we use, like really well-timed signals, GPS satellites and receivers, they have to take into account these relativistic effects when calculating position. Because they're moving very fast, they're also experiencing gravity differently, which gravity plays a role in all of this too, and we'll talk about that later. But otherwise, they'd be extremely inaccurate. So these things have to take into these effects. These are, again, this is a real thing. This is not pretend. This is not just some philosophical thing. This is real. This is how the universe actually is. Space and time are these bendable, fluid, flexible things. So I'll post a few other videos to explain some of this other stuff. I don't want to talk your ear off too much, but this idea of simultaneity is that two different people can disagree on whether or not two things happened at the same time or not. One person will say one happened and then the other happened. The other one will say that they happened simultaneously, and they're both right, which is crazy. Also, there's some cool effects if you're traveling close to the speed of light. So I'll post some videos. There'll be a game to play as well. And I don't know, it should be done with all this stuff hopefully by the end of the week. I don't know. I don't want to go too fast, but I also want to cover this stuff because it's neat. So, I don't know. I'll leave with that and cut you guys off there. Thanks a bunch. Oh, also, this slideshow is available under classwork if you look under the relativity tab. If you want to actually look through this slideshow to help you with whatever, you can find that there. Cool.